So now we have come to the third point, the problem of concurrency. So what is concurrency? The problem of concurrency. Concurrency refers to the problems that arise when working on many things at once in the same program. Concurrency problems originated in the operating system, which juggled many tasks simultaneously. Examples include virtualization, where the operating system runs multiple processes. Unfortunately, modern multi-threaded program also exhibits concurrency problems. Concurrency leads to deep and interesting problems that must be addressed. This is a very huge topic as well. So we have a multi-threaded program as well here, and thread.c, the same. This is also free. It is already saved in our computer. So we will see program creates two threads in this. What we will show you now. This program will create two threads. As you can see, pthread create p1 and p2, and program creates two threads using pthread create function. Threads are like function running within the same memory space, okay, within the same memory space with more than one active at a time. Each thread runs the worker. As you can see, we have a function routine here, incrementing a shared counter in a loop, okay. It will increment the shared counter in a loop. The value of the loop variable determines how many times each worker increments the counter. Okay. For example, when run with loops set to 1000, the final value of the counter is in question. It should be 2000. Okay, because we are giving 1000, then it should become 2000 when because we have two threads. Okay, we have two threads, so the final will be the addition of this p1 and p2. So this is void, this is volatile intel counter, zero integer loop, then we have the worker here, as you can see. So every time the counter loops, it will add, okay, the argument. So p1 and p2 is created. This is the loop. We have pthread p1 and p2, and it is created as it here. So let's go and see what it does. Okay, what we are going to do as usual, let's create let's go to our Unix. So just sign in, open the terminal, and let's do like this. Sorry. Okay, so the thread, what we are going to do, the concurrency list. As you can see, we have all the files, and GCC, this is a compiler in Linux, threads, okay, alf, this is the end threads.c, and thread. I hope it will work. Sorry. Sorry, GCC. Oh, I make mistake. Threads dots. Sorry, I took time. Threads.c, because we have thread.c, and LP thread. Okay, now what we are going to do, treats elf, treats elf, let's invoke it now. Now what we are going to do, we are going to invoke it, treats elf, and let's give an argument 1000. So when we give 1000, what we expect, the answer should be 2000, as you can see. Okay, no problem. Now let's continue and let's give 9000, for example. Threads dot elf 9000, for example. 18,000. Until now we are safe. Okay, again let's go and give treats for example, let's make it 10,000. So we expect, still we are safe. Okay, we expect that. Treats dot elf. Now let's give for example 100,000. Oh, you see, now 100,000, we expect 200,000, but as you can see, it is it's not giving us the same result. So let's continue, maybe treats dot elf, again 100,000. 3. You see, it gives us another result. Again treats dot elf 100,000, another result. Even the results are not the same, as you can see. Even the results are not the same. So this is the problem of concurrency. The problem of concurrency means a node, let's go to our so as we have seen now, what we have seen is a problem of concurrency. As you can see, odd and unusual outcome in the multi-threaded program relate to how instructions are executed, which is one at a time. So that is a problem. Incrementing the shared counter takes 3 instructions. The load instruction we have here, and the increment and the store again. So because of this instruction, the concurrency problem happens. Thus 3 instructions do not execute automatically all at once, leading to strange behavior. Like as you can see, we expect for this 100,000 twice, but the result we get was different. So concurrency is a problem that causes this behavior. So the second part of the book will address concurrency in detail. So I hope you understand, and I encourage you to go ahead and execute yourself the code, and you will see. So when the input value of set to n, we would loop, expect the final will be to n, but as you can see, the problem starts from here. So that is concurrency problem. Now the other issue is persistence. What is persistence? Persistence means every user, as you know, doesn't want to lose the file. Yeah? So the operating system should give us a guarantee for the user for the persistence. So a storage and persistence of a data. So devices such as DRAM means dynamic random access memory, store values in a volatile manner, because as you know, RAM is only 8 GB. So when some program wants to run in your system, the required data should be stored in the RAM first. So the CPU will, if in the CPU cache we have 3 levels, level 1, level 2, level 3 caches in the CPU. If the data is in the CPU already stored, no need to go to the DRAM. So the CPU go request data, fetch data from the RAM when it's executed program. So hardware and the data which is stored in the RAM is volatile in nature. You cannot save it. So that's not what the user need. So the operating system should provide us. So hardware and software are required to store data persistently. Hardware component input-output device such as HDD and SDD, solid state drive and hard disk drive, these two are very important, but SDD is taking the arena now very fast, more than HDD. I recommend to use SDD. So hardware components are some of the operating system used to store data persistently. Software component file system manage the disk and is responsible for the storing any file the user creates. In Windows we have NTFS system, in Linux we have ext4 file system. So file system is also a huge topic, it has its own topic we will discuss in data structures. So the operating system assumes that files will be shared across program or users, and it does not create a private virtualized disk for each program or application. So as the RAM, the memory and the operating system is the CPU are virtualized, the HDD or SDD will not be virtualized, okay? So it does not create a private virtualized disk for each program. This is very important. So to see this, we have another file, okay? We have another file, create a file. We are going to create a file in our temp folder that contains the string hello world. Now we will create this and we will see how the operating system persistently okay, this we have the file descriptor. So to accomplish this task, the program makes 3 calls into the operating system. The first, what we are going to do, we open and write and close. So we have open, write and close. So what we are going to do, the open call, open the create and create the file. The write call, write some data to the file. The close the file, indicating the program will not be writing any more data to it. Thus system calls are routed to the file system part of the operating system. The file system handles the request and return an inner code to the user. So what we are going to do, as usual, let's go to our system. Okay, let's go to our system and let's open our, this is Linux Ubuntu. Okay, so what we are going to do, let's clear this. And what we are going to do now, list the file. So what we do, I want to show you the man pages, okay? For the open, for example, the man page, whatever you need, this manual page, you have to go and check, okay? For example, if you go here, this is the open man page. So as you can see, open means open and possibly create a file, and this is how you have to enter in. This is int open, and this is the pointer, as you can see, and this is the one of the format. I think this is what we use in our system here in this book. Just press Q to go. Again, if you want to see man 2 for write, as you can see, write to a file descriptor. So writes up to count bytes from the buffer, starting at BUF to the file reference, and you can go ahead and read it. And again, I want to show you the man page for FS synchronize file synchronize. As you can see, synchronize a file in core state, and the description, what it does, everything you are allowed to go and check. The final what I want to show you is man to close, the close file. This is the close file directory, so closes a file descriptor, so the file descriptor will be closed. So what we are going to do now, ls the temp file. Let's go to see the temp file. Okay, temp file. So as you can see, this is the temp file. Currently we don't have, this is the file we have. So what we are going to do now, let's compile our GCC half. So we have the file, yeah, I showed you here. Yeah, IOC, this is the file. Okay, this is the file, and what we are going to see, then io.c. okay, okay. So what we are going to do, let's invoke it. io.elf. Okay, now what we are going to see, let's see the file temp. Okay, so as you can see now, we have the file is written already. So what we are going to see, cat temp file. I think I didn't make a mistake. Yeah, you see, this is hello world. So this is the file was written already. Okay, the file was written, so this is what it does. So in general, write data to a disk, and okay, so as we have seen, let's continue to our presentation. So writing data to a disk, the operating system performs two main tasks in order to write data to a disk. The first one is figure out where on disk the new data will reside, then issue input-output request to the underlying storage device. These are the two things what the operating system performs. The file system handles system crash during write using techniques such as journaling or copy on write, carefully ordering writes to disk to recover from failed writes. Efficiency is also important in writing data to disk. Input-output is lower than main memory access. The file system employs different data structures such as list and bit trees to optimize disk writes. So we reach here. Now the final is design goals. Let's go through and see what is the design goals. When we design operating system, what is the design goal? Operating system design goals. The first one, build up abstraction to make the system convenient and easy to use, provide high performance and minimize the overhead of the operating system. The operating system must strive to provide virtualization without excessive overhead, provide protection between applications through isolation. The bad behavior of one application should not harm others or the operating system itself. Ensure a high degree of reliability. The operating system must also run non-stop. Other issues to consider include energy efficiency, security, and mobility. Abstraction. Abstraction is the other thing. Abstraction is used to hide low-level implementation details and provide users with a convenient and easy-to-use interface. The operating system provides abstractions such as files, process, and virtual memory. Concerning performance, the operating system should provide high performance with minimum overhead. The operating system must manage resources such as CPU, memory, and input-output device efficiently. The operating system must also support different types of application, from a small embedded system to large data centers. Virtualization is the other type, and OS must provide virtualization without excessive overhead. Virtualization allows multiple instances of an operating system or application to run on the same hardware. Virtualization provides increased flexibility and resource utilization. Protection. The operating system must provide protection between applications. Isolation ensures that bad behavior of one application does not harm other or the operating system itself. Protection is achieved through mechanisms such as memory protection and process isolation. Reliability. The operating system must ensure a high degree of reliability. The operating system must be able to run non-stop without crashing or requesting frequent restart. The operating system must also provide mechanism for recovering from error or failure. Other issues: energy efficiency is important for mobile and battery-powered devices. Security is critical for protecting sensitive data and preventing unauthorized access. Mobility requires the operating system to support features such as wireless network and local-based services. These are some of the points, but we might need other advanced. We might consider some other advanced operating system features as well. So let's see the history of operating system. Some history. The first computer were large and expensive machines used mainly for scientific and military purposes. Early computers had no operating systems, and programs had to be loaded by hand via punch cards. In the 1950s, batch processing systems were introduced, allowing multiple jobs to be run at once. In the 1960s, time-sharing systems were developed, enabling multiple users to access a single computer simultaneously. Early operating systems. In 1950s and 1960s, operating systems were designed to manage batch processing and input-output operations. Some early operating systems include GEM, NAI, or this one, Fortran monitor system, IBM's operating systems 360. Thus, early operating systems were often tied to specific hardware and lacked many features that modern operating systems have. They lacked most of the features. Now, beyond the library protections, in the 1960s and 1970s, protection becomes a significant concern as more users and the process achieved shared resources. Protection mechanisms were developed to ensure that users could not access a resource they were not authorized to use. The concept of virtual memory was also introduced. allowing programs to access more memory than physically available. The code run on behalf of the operating system is different from the application code, meaning it is more privileged. System calls were introduced by Atlas computing systems, which makes the operating system control the process. System calls are not the same as procedural call. System calls arises the hardware privilege level using trap instruction to the more privileged level, we call it kernel mode. Kernel mode and user modes are different in use, in which user mode is a restricted mode of execution. So system call versus procedural call. Instead of providing operating system routines as a library, a special pair of hardware instructions and hardware states are added to make the transition into the operating system a more formal, controlled process. The key difference between a system call and a procedure call is that a system call transforms control into the operating system while simultaneously raising the hardware privileged level. User application run in user mode, which restricts what application can do. A system call is initiated through a special hardware instruction called a trap, which transforms control to a specified trap handler and simultaneously raises the privilege level to kernel mode. In kernel mode, the operating system has full access to the hardware of the system and can do things like initial input-output request or make more memory available to a program. When the operating system is done servicing the request, it passes control back to the user via a special return from trap instruction, which reverts to user mode, while simultaneously passing control back to where the application left off. The era of multiprogramming, where operating system really took off, was in the era of computing beyond the mainframe, that of the mini computer. In the 1960s and 1970s, multiprogramming becomes popular, allowing multiple programs to be run concurrently on a single machine. Multiprogramming operating systems include IBM's OS 360, Unix EC8, DSys, TOPS 10. These are some of the multi-programming operating systems. Those operating systems had features like time sharing, spooling, and file systems. Ability to execute multiple programs simultaneously by interleaving their execution on a single processor. Programs are divided into multiple small units and loaded into memory. Operating systems assign the processor to execute each unit in the time-sliced manner, allowing for a better processor utilization and increases overall system throughput. One of the major practical advancements of the time, the introduction of Unix operating system by Ken Thompson and Dennis Ritchie at Bell Laboratory. Unix took many good ideas from different operating systems, particularly from Multisys O72 and some from systems like TNX B72 and the Barclay time sharing system S68, but made them simpler and easier to use. The modern era. The personal computer or PC was a cheaper, faster, and more accessible alternative to the mini computer and was led by the Apple's early machine and the IBM PC. It is low cost, made it possible for individuals to have their own machine on their desktop, which eventually became the dominant force in computing. Early operating systems like Disk Operating System DOS from Microsoft was introduced but had a lot of problems, and the design was poor and no memory protection at all, and it has so many list of operating system features missing in this generation of the system. Fortunately, after some years of suffering, the old features of mini computer operating system started to find their way into the desktop. For example, Mac OS X has Unix as its core, including all of the features one would expect from such a mature system. Windows has similarly adopted many of the great ideas in computing history, starting in particular with Windows NT, a great leap forward in Microsoft OS technology. Currently, the introduction of Linux, Windows and Mac OS, Android devices and networks are some other cloud systems are example of current technology. The era of multitasking system, ability to execute multiple tasks or processes concurrently, allowing the user to switch between them seamlessly, achieved through preemption or cooperative multitasking. Preemption forcibly interrupts a running program to allow another process to run. Cooperative multitasking requires each process to explicitly yield control to the operating system after completing its task. Multiprocessor system, computer systems that has 2 or more CPUs, allowing multiple processors to execute simultaneously, provide higher processing power, better performance, and increased system reliability. Can be classified into symmetric multiprocessing and asymmetric multiprocessing systems. Distributed systems, collection of independent computers that work together as a single system to provide service to the user. Each computer operates autonomously and communicates with other computers using network communication protocol. Used in a wide range of applications including cloud computing, peer-to-peer systems, and distributed databases. Provide a benefits like high availability, fault tolerance, and scalability. The importance of Unix. Unix brought together many great ideas from early system and made a simple and powerful operating system. The unifying principle of building a small, powerful program that could be connected together to form larger workflows was the underlying concept of Unix. The shell provided primitives such as pipes to enable meta-level programming, making it easy to string together programs to accomplish bigger tasks. Unix was friendly for programmers and developers, providing a compiler for the C programming language, which made it easier for programmers to write their own program and share them. The accessibility and readability of the code was critical. Having a small kernel written in C invited others to play with the kernel, adding new and cool features. Companies tried to assert ownership and profit from Unix, resulting in legal wrangling among AT&T, Bell, Lab, and other players that cast a dark cloud over Unix. Many companies had their own variant of Unix, such as Sun OS from Sun Microsystems, AIX from IBM, HPUX from HP, and IRIX from SGI. So the legal wrangling slowed the spread of Unix, and the introduction of Windows as a dominant force in the PC market raised question about whether Unix would survive. This you can go, I encourage you to go and read from the textbook. History of Linux. A young Finnish hacker named Louis Torvalds decided to write his own version of Unix, which borrowed heavily on the principles and ideas behind the original system, but not from the code base, thus avoiding issues of legality. He enlisted help from many others around the world, and soon Linux was born, as well as the modern open source software movement. Most companies such as Google, Amazon, Facebook, and others choose to run Linux, as it was free and could be readily modified to suit their needs. Linux found a stronghold in smartphones too via Android for many of the same reasons. Steve Jobs took his Unix-based this next step operating environment with him to Apple, thus making Unix popular on desktop. Unix lives on, more important today than even better before. So guys, in short, I hope we have seen at this point you have an idea what is operating system, what is virtualization, what is concurrency, and persistency concepts, and we try to see the history of the operating systems, and we try to see the codes, how virtualizing the CPU, how to virtualizing the RAM, and we execute the code and persistency as well, and we try to see what is virtualization, how to virtualize the CPU, how to virtualize the RAM. We have seen it that when the two programs are running together, they were updating the same memory address, because the program assumes, each program assumes they are having their own memory, assigned memory. So by doing so, this virtualization technique, we are at this level. So to understand the operating system, these points are very important. So in the next video, we are going to start part 1 of virtualization, starting from chapter 3. So chapter 1 and chapter 2 is like this. Thank you so much, and see you in the next video. This is Engineer Selassie from Halo Academy and Brain Boosters. Thank you.